to give you some background, I used to actually be a professor at the University of Warwick in United Kingdom till 6 years ago. I moved back to Delhi, which is my home, after living in the United Kingdom for 22 years, with the intention of bringing machine learning and AI technology to customers in essentially India, but also the US and United Kingdom. So I founded Tatras Data as a starting point 6 years ago. And more recently, I decided that we can always do more. So I set up a foundation called Sarabjot Foundation, which is based out of Mohali, where we are providing training in machine learning and artificial intelligence, and specifically getting the students there, interns there, to work on social problems, right? So we work in agriculture, looking at how we can reduce the amount of pesticide being used by farmers. We are also looking at governance, so working with the Punjab's traffic police, looking at how we can actually optimize traffic within the state and city and reduce deaths on the roads. And of course, we work in education and in healthcare as well. What I'm going to talk about today, though, is an area that I did a lot of research in while I was in academia, the area of recommender systems. Everybody has used recommender systems, right? If you've been onto Amazon or you're a user of Netflix, essentially you'll see that their interfaces are driven by recommendation. You're always being told people who bought this also bought that, or maybe you like this because your friends have watched this, and so on. And so essentially what we are trying to do here is we are trying to navigate what is a huge catalog of information, right? So we live in a world where, of course, there are plenty of people that have nothing, but for those who can afford it, we are in a situation where you have more than you can actually consume, right? So we are essentially in a situation where we have too many items, but too little time to actually sift through those items and actually be able to consume or even find what we are interested in. And so recommender systems, and there are three different approaches essentially to recommender systems: content-based, collaborative, and hybrid recommender systems, essentially allow users to hopefully find things that are of interest to them. Now, one of the things you may have heard of is the filter bubble, right? So the idea that because now you're giving up control, you're actually telling the computer to present things to you that the computer thinks is going to be interesting to you. You are in a scenario where you've actually lost control on what you consume, right? What you wear today is probably influenced more by the fashion stores that are online, or even Amazon that is deciding what you should wear. We are all going to end up looking pretty similar by wearing the same stuff. We don't even know what's out there, because essentially the recommender system is putting in front of us the set of clothing or the set of books that we should be consuming, or in fact the news stories that are being put in front of us are also going to change the way we see the world. We won't know what exists outside of that bubble, right? And so that's a danger. From a technologist's perspective, we want to make sure that while we are providing useful content, we also want to make sure that we're doing some exploration, right? So you may have heard about the balance between exploitation and exploration, right? Typically, these are words that are used in artificial intelligence, and even more so in one aspect of artificial intelligence, which is to do with reinforcement learning, right? So the idea that you're searching in this space of possible solutions, and while you're learning as you search, and you're then using that to move in a direction that's going to give you better solutions, you also want to keep exploring other options, right? So that you don't miss out on potentially a path that you could have taken otherwise. And so in recommender systems, we really want to do the same thing, right? So let's look first at an example of content-based filtering, and let's take the news as an example, right? So we worked in building news recommenders, and of course, for those of you who are interested in text, the analysis of text is a huge area of research today, right? And it's a huge problem, because if you look at a particular news story like the one shown here, so we've got a Hindi article here that is to do with some kind of commotion caused at some kind of a rally in some part of the country, right? And it's about conflict between minority community and a majority community within the country. And if somebody consumes this news story, Really what we are trying to do is understand why has he consumed it, or why has she consumed it. Are they interested in Usha Thakur, who is the a BJP MLA that is being referred to within the story? Are they from Indore, because this incident actually took place in Indore? Are they generally worried about rising communal rhetoric within the country? So there are different reasons why we could consume this, right? And so typically what we want to do is we want to convert text, which is referred to as unstructured data. So it doesn't look neat like a table that we want to learn from, right? So you may have seen in machine learning, typically you're given an input, which is a table, where every record is the object of interest that you want to learn something about, right? You may want to learn whether you should give somebody a loan or not give somebody a loan, right? That's called structured data, because it's very clearly delineated in terms of the attributes with which we define somebody, right? So if you're asking for a loan, there'll be columns for every input data that you provide on the loan application, and then there'll be some kind of a label that says, should we give this person a loan, or was this person given a loan previously or not, right? And we are trying to learn that relationship. In text, we don't have that, right? We just have words, and words themselves are actually dependent on who's speaking them, right? So if I am speaking to you with a certain vocabulary that I'm used to, if Shashi Tharoor was giving the same talk, he'd be using a very different vocabulary, right? And so you'd end up with a scenario where exactly the same topic is being discussed, but the words are different. So in the early days, a lot of work that went into analyzing text and saying, let me recommend another story that is similar to this one, was looking for word similarities. And often that doesn't work, right? Because the author that is writing the story, there are multiple such authors, and they might be using a different vocabulary. So one of the areas where a lot of research has been done in machine learning is to say, how can we go from this, what is called syntactic representation? What do we mean by syntactic representation? It's the actual keywords, the words that are being used, the order in which those words are being used, right? That's really the syntax of the language, the grammar that's being used. So you have a syntactical representation, and then you have a semantic level representation about what is actually being communicated, right? And so there's been work in the area of saying, let me take the input, which is at a very granular level. For example, when we look at pictures, image analysis, the very dots that create the picture, the pixels, that's a very raw representation of data, right? And so in the early days, a lot of work was done on saying, how can I convert those pixels into interesting features that tells me whether there's a face in that image, right? So they actually did edge detection. The same way here, with text, what we are trying to do is we're saying that rather than looking at the words, let's look beyond the words, right? Let's look at the topics that are being discussed in there. And what is typically referred to as latent variable models, okay? So what is a latent variable? The term latent means one that is hidden in some way, right? It's not quite visible. So what we are doing is we are modeling the latent variables. So in text, typically a text document would be based on certain mix of topics, right? So in this case, the topic was to do with some jhamela happening between two communities. So those could be part of the topic representation. Some argument about whether people should be allowed to do certain things or not. All of those are different topics, right? So if I had wrote an article, for example, on cricket, and this was more to do with match fixing, then I would think of the topics behind the scenes being cricket. There might be some kind of financial transactions that are taking place, or finance. It might be about some cricketers being taken to court, right? So there's another topic of law enforcement in there, right? So rather than looking at the words, it doesn't matter if Kohli is involved here or Tendulkar is involved. It's the fact that it's cricket that is involved, right? So going away from the actual words and getting a representation at a topic level. Another thing that we have got pretty good at within AI is to extract information and be able to label it as being certain types of entities, a thing called named entity extraction, right? Or NER, or named entity recognition. So out here in this article, you should be able to see what's going on here. Okay, maybe I'm walking around too much. I should stay static. Okay, so in here you should be able to identify as humans. We are very quick at identifying this is a person, right? Or this is the place. We don't need to be told that. So again, we've created AI algorithms or machine learning algorithms that can read text and can identify in there the fact that Usha Thakur is a person, Navratri is a festival, that Muslim is a community, the BJP is a political party, Bakrid is an event, that kind of information, right? And that's called named entity extraction. So by extracting that from the text, we are now able to tag the text with very relevant content, right? To say that this is located in Madhya Pradesh, in the city of Indore, and we may want to also then be able to say that the topic here is controversial communal rhetoric, right? So that is a piece of topic modeling that I was referring to earlier. So what we would end up with when we do topic modeling is to say that rather than looking at the words, we have identified different topics within our text, right? So we take a large volume of text and we analyze that and look for common themes within them, right? So we might find that in our news articles that we've analyzed, we've got a topic called government unions. We've got another one called agricultural pricing, another one called cricket, and another one called weather, right? Now these are topics. These words may or may not appear in the news article itself. Now, what does that topic look like? Essentially, if we think of cricket, how likely are we to come across a word eggs or, bengan, right? Very unlikely. So what are the words that we're going to expect to see in there? We're going to expect to see ball, bat, pad, right? We may short leg, certain positions in cricket. So essentially, a topic is a probability distribution across words, saying how likely, is the word to appear within the topic, right? So if we are now going to generate a document where we say we want to generate a document that consists of cricket and match fixing, right? And the law, a court case basically that's going on about that, how would we do that? We would actually say, okay, the mix of words that are going to appear within my document is a mix of these three topics in some combination, right? So maybe 80% of the language is going to be about cricket, 15% is going to be about match fixing, and the third piece, which is to do with the court, is going to be around 5%, right? And now that we've decided on what is the mix of words and know how long a document we want to generate, how can we generate that document? We can randomly pick words from that distribution of words associated with a topic, right? And that is essentially a model for generating a document. Now, why am I talking about a model for generating a document? When I really want to learn about how do I take data and learn a model instead, right? Very often as data scientists or machine learning engineers, what we do is we create a model of the real world problem that we are trying to solve. What does that help us do? It helps us to define what is it that we need to learn. What are the parameters we need to learn? Okay, and then we actually build an algorithm that actually learns those parameters from the data. But if you don't have an initial model of what is the real world process and how it works, we're not going to be able to do that very successfully. It's something called inductive bias that you may come across, right? The idea that you're learning from specific instances, in this case, news stories. We want to learn a representation of those news stories. So we need to understand how would an author actually generate those news stories. Okay? And so the idea here is that with articles now that had very different words that were being used, as long as we were able to break that down into a very similar topic representation like the one that I've shown at the bottom here. So every document now is represented in this space of 11 topics. Suddenly our representation of this document is completely independent of words. It's just saying that the mix of topics in document D0 now is where it has a large percentage of words that are being generated from topic 6, a fairly large amount of data being generated or words being generated from topic 9, and then topic 4 and 5 also contribute to the document. Okay, the words are immaterial. What that means is now we can actually start matching documents that have a very different vocabulary but are actually talking about the same thing. Okay, so by doing this, what we found was that we were able to actually start recommending news stories a lot easier than we would have been able to do in previous models where we were just taking the text into account. Now, what I've given you as an example of one model of text where we're using latent variables, and those are called topic models. There are other algorithms out there. You may or may not have heard of word embeddings, which is, word to vec is another word used there, or glove vectorizers are another kind of set of words that are used to describe word embeddings. But essentially, they're neural network or deep learning models that essentially map every word in the language to a high dimensional vector of numbers. Right? Now, if I wanted to compare two words, right? So say I wanted to compare fly with pitch, right? Two different words. I can't actually say how similar they are, right? So fly, bee, and pitch are three words. Clearly, humans understand that a bee and a fly are both insects, and so they're similar to each other. But pitch is actually something to do with cricket, so it's not really that related to these, right? But for a machine to understand that is very, very difficult. So the way that these researchers have worked with this is to look at what words appear with other words, right? And so words that have a similar neighborhood across a very large volume of content, they must actually be similar, right? You've heard the saying that you're known by the company that you keep. Right? So essentially the idea behind these models is to say that if words keep the very same company, right? So a bee flies around, a fly also flies around, but a pitch doesn't fly, right? So the fact that you've got lots of references of bees and flies to do with flying around flowers, for example, they actually give us some indication that those two concepts are very similar. Those two words are very similar, right? So what word embeddings do is they take every word by analyzing a large volume of data, they actually map that into a continuous space. And once they are mapped onto a continuous space, they have coordinates in some n-dimensional space. You can actually compare them very easily. Okay, so all of these are essentially ways of representing words independently of the token that you actually see. Now, bee being there or fly being there is not so important. They're both mapped to a very similar space, and so we can actually say that they are very similar to each other. And so our representation becomes independent of the actual words that are being used. So in content-based filtering, we follow a very simple process. A human comes along and starts consuming some content, some news articles. Based on what they consume, how much time they spend on that, we actually create a profile of that individual, right? And then we start recommending other news stories or other content that is very similar to what they've consumed in the past. The problem comes when you have things like video, right? A few years ago, it wasn't possible to really analyze video and describe it as text. Of course, technology has moved on, so today we can actually analyze video, we can analyze speech, and we can actually do content-based filtering based on video and speech as well. But go back 4 or 5 years, and there was no possibility of actually doing that kind of analysis. So whenever you look at Netflix and what they were trying to do, they were essentially trying to say, well, you should watch this movie because your friends have also watched it, or people who have watched and liked movies that you have liked in the past have also liked this movie that you haven't watched. And so that kind of algorithm is called collaborative filtering. Essentially what we are saying is we are trying to automate wisdom of the crowd out here, right? So the whole idea is that a user, a human has gone along and rated a number of these items, given it numbers here for some of those items, and we are then able to say, well, this user can be represented as a vector of ratings for some of the items, the total number of items that are available, and we can then try and calculate the similarity of this user with other users, right? So we actually find similar users who have rated other movies in common with this user in a similar way. And then we can look at which movies have been rated by users in the neighborhood of this particular target user, and we can actually come up with what this user would rate that particular item as, right? So what we are saying is we are learning a function f here that for every user and item comes up with a prediction of what the rating is going to be that the user is going to give that item. Okay, so it becomes a regression problem. I don't know how much you've been introduced to these different terms earlier in the morning, but when you have, in machine learning, you're always learning a function, right? That gets an input and predicts something. If that input is a number, we refer to it as a regression. If it's not a number but is a category, right? Give somebody a loan, don't give them a loan. Then it is referred to as classification, right? But essentially, what is a function? A function is essentially got some inputs. It knows certain parameters that it incorporates with that data that you're giving to come up with the best possible output, right? And what do we mean by best possible output? We mean that we are getting an accurate prediction. So if this user has already predicted or given a rating to Star Wars as a 5 out of 5, then when we learn a function to rate Star Wars for that user, we should be close to 5, right? That's essentially what we are trying to do. Now, what do we mean by latent variables within this scenario, right? Or even before that. So let's look at two ways in which we can come up with a rating for this item. So this is one item here, and this is a user. We refer to this user as a target user. We want to figure out what movies is this person going to like? What should I recommend that they watch next, right? And essentially, so what we are saying is that the rating in this box here at the intersection of these two lines here is unknown, right? We don't know how this user is going to rate it. So if you think about it, there are two ways in which we can do it. One is, like I said, we can find users, other users along the rows. So every user is a row in this matrix. We could actually find users that have similar ratings with this user who have rated this item already. And we can take an average of that rating, right, of some kind of weighted average. And that will allow us to fill in this missing rating here. And if that is a high rating, if it's a 5 or a 4.4, then we are going to recommend that item to this user. Alternatively, we can actually, and this is called user-based collaborative filtering. The alternative is to say, well, this is the item. How about I find similar items to this instead, right? And I want to find similar items and take the average rating for the items in the neighborhood of this item that have been rated by this user, right? So if all these users have given ratings for this item here, they've also given ratings for this item here, we can calculate the similarity between those two. It so happens that this item was rated by this user as a 4, but this user has not rated the second item here, right? So we could actually say, well, this item is very similar to this item across all users' ratings. So we can pick up this rating for this user and put it here as well, right? So there are two different ways in which we can actually come up with this rating. This approach of finding a neighborhood of items is called item-based collaborative filtering, okay? So these are the basic algorithms for collaborative filtering. Now what are we going to do is we're going to say, well, actually a user never rates a movie sitting in a bubble. There's a reason why he rates that movie high or low, right? So this particular user, his reasons might be that he's very keen on good cinematography or special effects. He might be a follower of a production house like Dharma, for example, right? Or he might like a certain genre of movies like action thrillers, or maybe interested in a particular actor, for example, Amir Khan, right? So really, we don't know these implicit reasons why the user is actually giving this rating. All we know is that there were certain items consumed and these were the ratings given. So what are these? These are again examples of latent factors, right? And so what we want to do is we want to try and find out from just this data where we are told that this user has given ratings to these items, what are the real reasons why this user has given these ratings. Now what makes this more complicated again is that imagine that this user has a couple of children, and when he goes to watch movies with his children, of course, the drivers for what is a good movie changes. It suddenly becomes animation. Maybe Disney is now what is interesting to this individual, or Pixar, or action heroes or comedies, right? And so suddenly now we have this kind of behavior where there are two different aspects to this user. And of course, he never tells us, right, that I'm watching this movie with my children, right? So you actually have different latent variables in different contexts, right? So contextual recommendation is an area where research is quite active currently, right? Saying that understanding the context is really important. And as you can imagine, based on what I've been saying up until now, context itself can be a latent variable, right? Typically, when we think of context these days, or at least in industry, we take the easy path, right? We say location is context. So if you're walking with a mobile phone and I'm in Gurgaon right now, I may be interested in something different to if I'm in Delhi or in Noida, right? Yes, of course, that's context, right? If I'm driving, so if I'm moving quick enough, and again, I can get access to that by the GPS signal from my mobile phone, then maybe I want to switch from, you know, he may have been reading an article and started driving, suddenly my audio should switch on automatically and start speaking that news story to the individual instead, right? Again, contextually, we are deciding how to interact with this user. But that's only part of the story, right? And so rather than taking the easy path, we've got to start thinking about if we really want to recommend to the individual, if we want to deliver content to the individual that's really going to be of interest as a service to him, we really need to get down to the point of understanding what are the drivers to the behaviors that we are seeing, right? When we go to a doctor, what does the doctor do? The doctor can see symptoms, can measure the symptoms. He can't measure the disease. But what does he do? He treats the disease, not the symptom, right? So that's also a latent variable within what he is measuring. So typically what we are measuring and what is visible is not what we want to deal with. We want to deal with what are the drivers behind that, right? And so latent variable modeling, not just in recommender systems, but in general, right across the board, is a very, very important aspect. And I just thought that within recommender systems, of course, you can relate to this because this is a service that you work with, right, on a daily basis pretty much. So when we think about this matrix here, another thing to remember is that essentially we live in a world of plenty, right, is what I started off with. So essentially, if we look at the catalog of Amazon, there are hundreds and thousands of items out there, right? What does the typical user consume? The typical user consumes less than 1% of that, right? So this is what is called a sparse matrix. Most of these elements of this matrix are going to be empty, not zero, because zero means I don't like this at all, right? They're empty. We don't know what the rating is. They haven't rated it. So we have a very sparse matrix here. And so one of the first attempts at trying to get to this point of understanding the latent variables was to do matrix factorization. You've heard of factorization before, right? In school, we were laboriously made to say, you know, what are the factors of 12? Or what are the factors of 27? And we had to look at the prime factorization. It's the same idea here. So what we are saying with matrix factorization is that we are essentially wanting to convert this rating matrix R, right? So this rating matrix R is the matrix you were seeing on the previous slide. And we want to split it into a P matrix and a Q matrix. And when we multiply the two, what do we want to do? We want to get back this R approximately. Okay? And what are the dimensions of the P and Q? So if we have U users and I items, then P is going to be a U by D matrix, right? And Q is going to be a D by I matrix. So you know when we multiply matrices, and if you don't know that, then you're probably in the wrong space if you're trying to get into machine learning, right? Machine learning requires a lot of maths, and linear algebra is a very important part of that, and probability is the other really important part of that, right? So if you, you're trying to essentially understand users and representing them in the dimensions of D. What are those D? D are your latent variables, okay? So essentially, if you can multiply these two, a magical thing happens, right? The magic that happens is that in the original data, if you had missing information, no ratings because these had not been consumed by the user, once you do the matrix factorization of this, you now have P and Q. And P and Q these matrices here are in lower dimensional space, right? Because this is U by D and D by I. When you multiply those two, what you get is a non-sparse matrix of ratings. Okay, so what you end up here, for example, when you multiply the decomposition of this matrix, is you get numbers in every cell here. So it's not sparse anymore. And if we were trying to make a prediction for U4 here, right, so we could recommend any of these 3 movies that they haven't consumed already. By multiplying, first doing the decomposition of this into P and Q, and then multiplying the P and Q, we actually get ratings in here. And we can see that I4 now has a rating of 4.84, right, this one here, which earlier we didn't know. And these other 2 items that we didn't have ratings for are getting a very low rating. So what are we going to recommend to this user? Clearly, we're going to recommend the 4th item, I4, right? And this magic that's happened is basically looking at when we split R into P and Q, we are looking at the statistical properties of interactions between items, right? And so we are actually learning a way to predict these numbers here that we didn't know earlier, right? And that's really cool. So suddenly from nothing, we've got something. Okay, so again, I've used a complicated word here called regularization, and I've talked about a cost function right out here. Again, are these terms familiar to you? Have you been exposed to these things today already? You have, right? So essentially, all machine learning is search in some space of parameters. What are the parameters here, do you think, that we don't know? The parameters here that we don't know are the values within P and Q, because we don't know those, right? We don't know how important the different latent variables are to the user. We also don't know how important or how good is an item at fulfilling the desire of people that have an interest in those latent variables. And that's what P and Q represents. Okay? So what are we doing here is, what we are saying is that we want to minimize the error of prediction of the ratings that we have in R. And what is our prediction? Our prediction is the product of the right row and column of the P and Q matrix that gives us the rjth value, right? So how do we get this value here of 4.84? We are taking the 4th row of the P matrix and multiplying it by the 4th row here of the Q matrix, right? Fourth column of the Q matrix, right? And so by multiplying those two, we are now getting a prediction. Now, what we are saying in the cost function is that for ratings that we know, like this 4, we want to make sure that the 4th row of P, when multiplied by the 3rd row of Q, comes very close to 4, right? So the ratings we know, we want to make sure that we don't get error in those. So that's all we are saying there, right? So we're trying to minimize that error of known ratings when we do a multiplication, and we're doing a search in the space of all possible values that we can put into P and Q. Now, what is regularization? Regularization is a rather complicated name for something very simple, right? And what is that simple thing that we are trying to do? We are trying to make sure that we don't do rote learning. We have a small amount of data. We are trying to learn a lot of parameters. In that situation, what can happen is you learn by memorizing, something that we were trained to do in school, right? Now we are saying don't do it. It's kind of late in our lives to be saying that. But rote learning, we always knew was wrong, right? Why is it wrong? Because if I tell you that 2 plus 3 is 5, and that's all you learn, and then I ask you what is 4 plus 5, you won't know the answer, right? Because you only know what you were taught. 2 plus 3 is 5, right? And so you'll not be able to generalize to problems you haven't been, if you haven't learned the concept of addition, right? So here also in machine learning, the most important thing is to generalize to data we haven't seen before. And what are we saying there? We want to generalize to being able to predict ratings that we don't know, okay? And so regularization is essentially this term here. I won't go into details of what this is, but essentially what we do is we start dampening down real great desire that an algorithm may have to move in a direction it thinks is a good direction to move in, right? So if you're in a mountain range and you want to get down to the bottom and there's a cloud cover, right? What would be the approach you would take? The greedy approach would be to say, I can see my feet and I can see the land around my feet. The direction that's going down really quickly, that's the direction I'll take. Why? Because that's going to get me to my objective quickly. What's going to happen then is you're going to walk off a cliff and kill yourself, right? Typically, that's what's going to happen. Well, that's a bad thing. Agreed? So what you're saying here as well is for the algorithm, if it finds a direction to move in to minimize the error, which is looking too good, dampen down its belief that that's a good direction to move in, right? And so that's what regularization does in a very kind of generic, kind of high level. That's exactly what we are doing. So we've seen how important latent variables are, and we know how now to represent text in this latent space. We know how we can do collaborative filtering in that latent space as well. Now, we were in a situation where we had to build a recommender system for a news provider, and typically you can't use collaborative filtering to recommend news. Why can't you do it? Because there's a problem with collaborative filtering. The problem with collaborative filtering is if you get a new item, a new news story that has to be recommended, right? And nobody has rated it, it can't be recommended. Okay, and that's called the new item problem. So why can't it be recommended? Because somebody has to consume it and give it a rating for us to know whether it's good or bad, right? And then in their neighborhood, the users that have actually rated that news story, we'll start recommending it. So we need a hybrid approach to recommendation there. And so what we did there was to say, well, rather than representing items now, we will represent users in topic space, right? And so up here, rather than having individual items, the latent variables that we found, the topics that we found representing news stories, is what we used instead. And the good thing about that is that any new news story is going to essentially use the same underlying topics, right? The vocabulary might be different, the scenario might be different, because some breaking news is now about some political mayhem that's taking place. But essentially, the topics are going to remain the same, right? It's a political story. These are the basic actors in there. It might be, politics, therefore BJP, Congress, whatever else. These are all topics in the document. And unless something really spectacularly different happens, where a new topic suddenly emerges, we should be able to actually represent a document in that latent space that we've already learned, right? And with that, we can then start making recommendations. Another issue that often plagues us is this filter bubble that we talked about, right? So the filter bubble we said was where I might actually read my first news story. It so happens that it's a politics news story. If I then decide that if the algorithm then decides that this person is only interested in politics and starts giving only politics stories, all of my other desires are not going to be fulfilled, right? And so typically what these news websites do is they say, okay, we won't recommend until somebody has consumed 20 stories, right? Because then we are assuming that people are finding different, diverse set of stories, and they're giving us more information about what they're interested in, and so we get a generic idea of their interests after 20 stories have been consumed, and then we'll start recommending. What's the problem with that? The main problem is that we all have a very small attention span today. So if we go to a service and start consuming a service, and we don't get what we are looking for, we ignore that service. We only give people one chance, right? We've become very non-forgiving in that sense. So most people don't get to a point where they've consumed 20 stories. And if they haven't consumed that 20 stories, and we can't recommend something to them that is going to be interesting, then we've lost that customer, okay? And so what we did here was, we said, okay, hang on a second. We can do better than giving a static interface, right? So what we calculated was an average Joe. What do we mean by average Joe? We looked at group behavior. trending stories, right? Again, that's nothing spectacular. We're looking at trending stories. What are people consuming? Things that are being consumed are actually being represented and presented to the user. Now, in addition to that, what we said was, well, whatever the user has consumed, let's start giving it a little more weight and adding it into that average Joe behavior, right? So now what we are saying is, as people start giving us a signal, slowly we go from getting recommendations as an average user to actually getting recommendations that are in some way skewed towards what we have consumed, right? And we then start also looking at the neighborhood of the user. So collaborative filtering coming in here again. And we built up this fairly interesting piece where the neighborhood only became important into the recommendation once we started getting a signal from this user that was actually pretty strong, right? And so we actually mixed the user's profile with the neighborhood profile, and with these weights that we learned over time, we actually decided to start moving different users away from the average behavior in different pathways or in different times as they started consuming, right? So I do realize that I'm running out of time. Now, one of the things that I wanted to also bring up with you is that with the recommender systems, when we're dealing with recommender systems, we've talked about predicting the ratings, right? Always talk about predicting the ratings. We know, however, that just predicting the highest rated items to somebody may not be the best recommendation, right? So if all of my recommendations are very similar to each other, right? So say somebody consumes a video to do with Kohli and Anushka's wedding, right? And so my recommendations are going to be all about Kohli and Anushka's wedding. That's not going to be very useful, right? We want to create diversity within what we recommend. So rather than just saying those that have the highest predicted ratings, we also bring in a piece to the algorithm that says, well, actually, the second rating is very similar to the first one in content, so let's actually skip that and go to something that is less similar, right? So we're creating diversity in the recommendation. And the idea of this here is the fact that, Leicester City, a fairly not well-known football team, won the championship, the premiership in the UK a few years ago. And the idea being that, players, individual players that are very good, if we start creating a team of very good individual players, they may not work well as a team. So similarly with recommendation, the focus has always been, and this is actually all Netflix's fault, right? Because a few years ago, they actually came up with a challenge where they put out a data set and said, if anybody can improve the rating accuracy by 10%, we're going to give them $1 million. And so everybody focused on that. The research community also focused on that, and rating prediction became the most important way of looking at recommenders. What I'm trying to say here is, let's pull back from there now. It's been a number of years since that money was won. And interestingly, Netflix never actually implemented that solution. They never used that, right? So it was basically a great marketing stunt by them. But now we've got to start thinking back again about, rather than rating prediction, let's start giving people diverse recommendations. I can stop here because I've kind of gone through a lot of information here, or if you give me 5 minutes, I can just give some other examples. Is 5 minutes good? Okay. So to now take you away from news stories and content and collaborative filtering and content-based filtering, I want to give you a different view on things, right? So in fashion recommendation, one of the biggest challenges that we had when creating a recommendation system for fashion, which is currently being used, by top brands like, Marks and Spencers and Topshop and so on in the UK, was to actually generate features of interest, right? So rather than using just collaborative filtering and content-based filtering, which this company was already using that had built the recommender system, what we did was we said, well, hang on a second. Let's just look at the behavior of users, right? So we actually had users here that were, so this is sales data, right, for different products. Each of these colors is sales data. And what we found was that different products have different behaviors. For example, this product here, is a fairly staple product. What do we mean by staple? That the amount of sales after its launch is fairly constant, right? And it has a long life out there. So, maybe something like blue jeans, right? Everybody loves blue jeans, over generations. You always need blue jeans. There are other ephemeral products that are just fashion statements, right? Some celebrity wears a dress at award ceremony, and suddenly everybody wants to wear that dress, right? And after a week, nobody really wants to wear that dress. And so they come in a burst and disappear. And then we've got seasonality within sales as well. So if this was actually maybe a coat, then we need a heavy coat only in the winters, and so we have these different patterns of products, right? So rather than just treating every product the same as collaborative filtering does, we decided to actually take into account the kind of product and actually start recommending there. Now, what is also very interesting is the fact that when we overlay individual users' purchase patterns on the overall purchase patterns of the products, we find some interesting behaviors, right? So some users will, you notice in this ephemeral product, we had this huge boost up here of sales, and then it actually had a second life here, right? So people who buy very often in that second life are price sensitive people who are not really interested in looking like Anushka Sharma necessarily, but are actually saying, well, I don't mind wearing that dress, but at the right price, right? And so they're sensible, purchasers who actually, so there's no point in recommending this product to them while it's in this phase here, right? So the idea of saying, well, let's just make the recommender trail the behavior of the person that we are recommending to. Here is somebody who's got eclectic taste. What do we mean by eclectic taste? These are people who don't follow trends. So products that are not big sellers, they're actually interested in buying those, right? So they are, again, people that you wouldn't want to recommend trending products to, because they're just not going to be interested. And then you have the fashionistas, people who actually start to buy the product the moment the product is going to go ballistic here in sales, right? So they're catching it at the right time. And the follower is the person that's buying that product as it comes down out here, right? So these are people who are very confident potentially about their fashion, and therefore the moment they see something, they understand that this is going to be a hit, and they want to be on Facebook in that dress first, right? So you've got to actually recommend it to them. And of course, they'll never wear it a second time either, right? But that's on an aside. So by creating these features that we extracted from the data, and of course, if you hear a talk by a deep learning expert, they'll say, oh, you don't need to do feature engineering anymore. Don't believe them. You still have to do feature engineering, right? In certain domains, like image analysis, you don't need to do it, because deep learning actually does a great job of doing that, right? And how has deep learning started doing that? They've learned from people who did feature engineering for years before that, right? And now they don't give them the credit for it. So it's a very, very important aspect. More complex domains like adaptive learning, where you're trying to actually find an individual path through content, right? So you have MOOCs. Everybody wants to be on a MOOC these days, right? Everybody's done Andrew Ng's machine learning course and has learned nothing out of it, right? So what we want to do here with adaptive learning is to say, well, actually, we want to find a different path for everybody. If I do machine learning by Andrew Ng and you do it also, or I started saying Ng too, Andrew Ng, right? We'll be taken through the same content the same way. But I've actually been doing machine learning for 25 years. I don't need to know everything. Maybe there's some aspect that I'm interested in, right? So rather than taking me through a path that will put me to sleep in the first couple of hours, find an individual path, right? So here we used Bayesian belief networks instead. I won't go into the details of that, but essentially, why did we have to use this? Because there are dependencies between content there, right? So if you're trying to recommend content, we want to make sure that we understand the proficiency of the student in prerequisite content before we start giving them complex content, right? So that's another piece that we've done here. So I'll conclude here. Apologies, as usual, as I was saying to you earlier, that whenever I get a mic, I go crazy, right? I start talking and I can't give up. So hopefully that's given you insights into latent variable modeling, which is a really, really important aspect of machine learning today, and a flavor of recommender systems. And whenever anybody says to you, well, recommendation is a solved problem, then just walk away from them. Don't take a job with them. Okay, because what they're assuming is that collaborative filtering and content-based filtering solves every problem. It doesn't. Okay, and I haven't really wasted 10 years of my life doing recommender systems. There is a reason why you have different domains requiring specialized solutions to them. Thank you very much. Questions? Questions? Go on. Okay, so essentially, if the algorithms we talk about, I mean, we typically write algorithms in Python. We deploy them in different ways, right? Depending on the volume of data that we need to consume, right? So you would get into, typically once you've created your recommender system, you deploy it with a RESTful web service, for example, where the volume is not very large, right? And so you're hitting that RESTful web service directly. If your volume is very large, you need to analyze this in Spark instead, the data. And build your models so that they can actually take into account streaming information, right? So there you'd be looking at Spark streaming as the basis for deployment. See, we don't get into visualization too much. So for us, using something like Matplotlib and Seaborn is fine. We don't typically go into doing fancy visualizations using query and reporting type tools, right? So we don't do that. Our focus very much is on the hardcore algorithmics rather than looking at visualization itself. Any other questions? Okay, well, I shall thank you for being so patient and not falling asleep. I don't see anybody who's fallen asleep after lunch.
Thank you, sir, for sharing abundant knowledge. I'd like to hold you for a minute.
Okay.
Yes, sir. I request Dr. Ritika Vasan to give a vote of thanks to Dr. Sarabjot Singh.
Sarabjot.
Sarabjot, my bad, sorry.
Thank you.
Thank you so much.